Hi, so in this video we will finish this long proof that we were working on in the previous video number 7. So let's see, at some point we were able to get a conjunction on line 8, and that is always a good thing because you can break a conjunction apart by the rule of simplification. So let me see if I can put back on the rules. So remember, simplification right here is the rule that allows you to get either side of a conjunction. So from P and Q you can always derive P, and also you can always derive Q. So that's just what we did in steps 9 and 10 here in our proof. And then we brought down if PA then QA by instantiating the first premise, and also since we were doing that we did it for the second premise as well. We instantiate to A, of course, so that we can work with all these formulae. They're all in the same constant. And remember, the constant A was first introduced into the proof in line 5 when we applied existential instantiation for the first time. Should be clear why we went with existential instantiation first. If we had used universal instantiation first and had instantiated to A, then because of the restriction on existential instantiation, we would have had to instantiate line 4 to a different constant. We would have had to instantiate it to B because A was already in the proof. But then we would not have been able to work with all these formulae together. So the key here is to use first existential instantiation, introduce a constant into the proof, and then when you use universal instantiation on the formula that have a universal quantifier, then obviously you instantiate to the same constant that you introduced with existential instantiation. So now everything is expressed in terms of A. It's much easier to work with these things. So we got a bunch of lines here, and it looks like we can do quite a bit with them. Look at lines 9 and 11. Isn't that an easy modus ponens that we can do? Remember modus ponens? It's the rule that when you have a conditional, if P then Q, and then you have a formula that is just the same as the antecedent of the conditional, you can infer the consequent of that conditional. And that's exactly the situation that we have. Here we have a conditional. If PA, then QA, it's here in line 11. And then we have another line that is the same as the antecedent. So we can infer the consequent by modus ponens. So in line 13 here, we will say QA by lines 9 and 11 modus ponens. 9, 11, MP for modus ponens. Oh, but look, now we got QA, and we can do the same thing over here with line 12, because line 12 is also a conditional, and this is the antecedent, QA, and again we have a match with line 13. So by modus ponens, we can infer this stretch here, RA and not SA, and this will be 13 and 12 modus ponens. Okay, and now we're very close, because by simplification we can get RA. line 14, simplification. And now we have our contradiction. Do you see it? This line and line 10. Line 10 has not RA, and line 15 has RA. So that means that by assuming the contrary or the negation of the conclusion on line 3, an absurdity followed from that assumption. We unpacked things from there, and we ended up both with not RA and with RA. That's a contradiction. So we can exhibit that by using conjunction and making a formula with that contradiction. So RA and not RA by lines 15 and 10 conjunction. Okay, so now this subderivation, this proof in the proof, if you will, is complete. We showed that the assumption on line 3 is absurd. It leads to a contradiction. So on line 17, you can enter the conclusion. We showed that not for all x, if p of x, then r of x is impossible. So since it's either not for all x, if px, then rx, or for all x, if px, then rx. So a statement, either a statement or its negation, is true. We proved that the statement on line 3 cannot be true. So the negation of that statement must be true. And the negation of not for all x, if p of x, then r of x, is for all x, if px, then rx, which is the conclusion of the argument. So we can cite here the subderivation. So we can say the lines 3 through 16 and indirect proof show that for all x, if px, then rx is the case if the two premises at the beginning are assumed. This concludes our proof, and so we proved it through this kind of indirect method. I hope this video was useful. Thank you very much for your attention. Sorry I had to make two separate videos, but it's a long proof and there was a lot to unpack. Thanks.